So hello everyone. Today we are going to continue our journey to the machine learning with Python. So today's major topic is about supervised learning. So yesterday we talked about like 3 types of machine learning, and this is more like the major topic of today or even of the workshop, because supervised learning is like the most frequent question we face from day to day. So for the agenda, we have passed day 1, and today we are going to talk about classification. And I was originally planned to talk about regression, but I think today's topic is kind of long. So I will move the regression and the regularization to day 3. So because I think when we finish the classification, those things could be quite easy and will not take much time. So for these slides, still we use this arrow to denote the code line or pseudocode, and anything with an underline is a hyperlink. And as usual, we will teach this workshop not like have some kind of breaks in the middle. I cannot teach for 3 hours, keep talking for 3 hours. Yeah, that will kill you and kill me. So we will have 45 minutes first, and then take a 10-minute break and so on. The topics today will be the very classic and also some hot topic of classification algorithms. And during the classification algorithms, we are going to talk about the performance measure and also about the overfitting and underfitting issue. And then lastly, we go to the Jupyter notebook to do some practice, like to try to use those packages, like using every classification algorithm to finish simple or not simple task. As a recap, yesterday we learned what is the machine learning, the definition. So it has 3 components: the experience E, the task T, and the performance measure P. And the experience E is usually data, and the task, as we said for today, is the supervised classification. Performance measure P is what we are going to learn a little later. And for the 3 types of machine learning, we understand what is unsupervised, what is supervised, and what is reinforcement. And we also have a good understanding about the big picture about when we training a model, what we are actually doing. And for more details is that we know, okay, in the machine learning, when we build a machine learning model, we have this training and the test set. For training, we used it to build a model, which we will cover today, like use a lot of training, like use the data to train a lot of models and use a test set to evaluate whether this model is generalizable. We learn what is the loss function, that is to try to measure how bad this model fits the data. And we have seen one like a cartoon example about overfitting and underfitting. And also we talk about what is the hyperparameters. And if we want to find the best hyperparameters, what should we do using a cross-validation? Lastly, we talk about challenges in machine learning, like machine learning is not a good medicine for all disease. You need to like be careful when you doing some machine learning practice, and try to find a solution for your specific problem. For practice, we already know how to use Jupyter, how to use some useful library, like how to make plots, how to use the NumPy array, make a matrix. And we lastly, like yesterday, we tried a very simple supervised learning example. So I don't know like if anyone have any problem during like our last workshops contents, but if you don't understand, here is a good thing from Angel Ng, so which is a famous professor at Stanford, that he always saying, don't worry about it if you don't understand, things will move on. So for the three types of machine learning, in this workshop, we mainly talk about these two, the supervised and unsupervised. And based on the labels, we can further classify the supervised learning into the classification problem or regression problem based on whether the label is a categorical label or it's a continuous label. So for the classification, for the supervised learning, we basically have this particular data type that we have n samples, and each sample have d features, and each sample will also have a label. So what machine learning do is trying to find a function that can generate or predict y based on the input x. So here are a list of different machine learning algorithms, the different choice of that. For the classification tasks, as we have said that classification task, your target y, it's a categorical variable like 1 and 0 or 2, it's like a discrete. So here is what we are going to learn today. So in total, there are like 5 and 4, so nine algorithms, and some of them are very classic machine learning algorithms, like the top 4, and then some of them are the tree-based machine learning algorithm. Some are the boosting, so which is a very interesting tool that can enhance the machine learning performance. And another thing is the most hot topic recently, neural network. So all of this machine learning algorithm is trying to predict y based on the x. And our target or our loss function is always try to compare the predicted y with the true value y. We want to make the prediction as accurate as possible. So yeah, this is again goes back to the definition to the machine learning, that we want to increase the performance measure as we learn from the data. So first, let's dive into the first one, logistic regression, which is a very classic and a very kind of simple idea that we have this model that generates a probability P. And this is just using a sigmoid function that the linear combination of all your features, x transpose times the theta. Theta is the parameters to learn. So after you transform using this sigmoid function, it will give you a value between 0 and 1. So the y hat will, based on this 0 and 1 value, if the predicted probability less than 0.5, we will assign them with the value 0. If it's greater or equal to 0.5, we will assign with 1. So this is a very classic binary classification problem. And from the name logistic regression, we thought it's going to do some like a continuous prediction, but here actually what we did is trying to use it for classification. So here we can notice that the underlying mechanism actually is still a linear model, that you find a linear combination of features to make the decisions. So if we plot the decision boundary that we want to classify classify all the samples based on the probability, like based on the p smaller than 0.5 or greater than 0.5. So we will have this decision boundary, which is shown in this dashed line. And for the left of this decision boundary, we will have this part to be labeled as 0. Now for the right part, it's going to be predicted as 1. So as we can see, some of the samples is not correctly classified. If we see this blue triangle is a true label, and the left of the boundary is a predicted label, we can see some kind of like although it's true 0, but it's predicted as 1, and also some like the true ones predicted at 0. So still like the classification, the accuracy will not be 100%. So based on this this model, we can write out the loss function. So for a particular sample, if it's if the truth is 1, we will write the loss function or cost function as negative log p hat, and on the contrary, we will write as this. So combine them, we can generate the loss function for all the samples that we take the average. So if we take a look at this formula, it's only this part is equivalent to the above formula. Just trying to write 2 lines into 1 line. So for example, when y equals 0, this part will be 0. So we will end up with log, this will be 1. We will end up with log 1 minus p. So which is similar as this part. And when y is 1, this will be 0, and we end up with log p hat. So as this part. So this is like the loss function for logistic regression. And if we want to generalize it to multi-class, we will have this sum of k equals 1 to k to capital K, which denotes to the capital K classes. And yeah, I think this is all about the logistic regression. We talk about the model itself and what's the loss function. And based on the loss function, we can write a program. Although we don't need to explicitly try to write out the loss function, but the algorithm or the package, what they do is try to minimize the loss function. So based on this logistic regression, I want to mention the performance measure. So when we talk about how well the algorithm works, we want to use some quantitative value to denote, okay, whether this is a good classifier or not a good classifier. So one direct measurement is the accuracy, which is the true positive and the true negative, like how many answers we have, we make it correct among all the samples, like the sum of TP of P, Tn, Fn. So true positive, false positive, true negative, false negative. So the TP here is just denoted as this. They are labeled as 1, and they are like correctly assigned with 1 because they located on the right to the decision boundary. And similarly, this bottom left is the true negative. So this will give us somehow reasonable measurement, but here is a question that is this measurement always good? So anyone, do you know like if we should always use the accuracy to claim we have a good classifier? So I think I can just directly give the answer. So just consider a case that we have 90% of samples to be 0, and only 10% of samples to be 1. So I can just write a single line of algorithm, like we always predict 0, no matter what input it is. So in that case, we always have this 90% of accuracy, and we achieve the best speed, right? Like any other algorithms cannot beat our algorithm because we only run this printf statement. So this accuracy is kind of risky when you have a very skewed data set, like you have a very unbalanced data set. So this is also something we should keep in mind whenever you read a paper or you listen to a talk. They claim, okay, our accuracy is it achieves 90%. That doesn't necessarily mean the algorithm is good, because you should consider what the data set looks like. So in addition to the accuracy, there is another good performance measure, which is called the confusion matrix. So basically, as we said, we have the true negative, true positive, and we have the predicted negative, predicted positive. So basically, we can classify all the samples into these 4 sections. So any sample will fall into one region in this figure. So the precision, so based on this matrix, we can calculate the precision and the recall. And the precision and the recall is more accurate, like they can take care of the imbalanced data set. And usually they are more preferred than accuracy when you have a skewed data set. So the precision is just like among what the predicted positives, how many of them are true, and the recall is that among all the positives, like the actual true positives, how many of them are true. So this is like the 2 cycles in this graph, and the F1 score is another usually use the metric, which is just a harmonic mean between precision and recall. So yeah, these are the important concepts for the machine learning assessment, and we are going to practice them in the Jupyter notebook later. So right now we have the fixed boundary, like we have a fixed threshold, whether they are greater than 0.05 or smaller than 0.05. We can get this confusion matrix and then calculate the accuracy, precision, recall. But sometimes we want to change the threshold to get another level of performance measure. So this is sometimes called the precision and recall trade-off. So basically, if you think, okay, we move the boundary to the left or to the right, the precision and the recall will change accordingly. So when they change, like when we have a decision boundary at one point, we will have a precision and a recall. So the right figure will show at the threshold changes what the precision and recall will behave. So we can see one goes up and one goes down. So there is they are counteracting with each other. There is no way to achieve both goes up. So if we just plot the precision against the recall, we probably will see a plot like this. So this is also called the PRRC, precision recall ROC. So what is ROC? It's it's an abbreviation for the residual operation characteristic curve. So yeah, this is a long name, but you just need to remember when we change the threshold, and then from one direction to the other across all the possibilities, we will have this kind of curve. So another curve is the ROC itself that tries to measure the false positive rate and the true positive rate. So in this curve, a good classifier should have a really like the perfect classifier should be just like this. The edges like they are like showing like triangles in, and the random classifier, like you are doing the random guess for each instance, new instance input. So basically you will force into this dashed line. So basically this, well, a good classifier should be the top left on this figure. And sometimes we calculate a measure called the curve, the area under the curve, so which is short for AUC. And the greater the value of AUC, the better the performance will be. So so far we talk about the logistic regression algorithm. We know what is the cross entropy loss when we talk about loss function in logistic regression, and we also covered the performance measure accuracy, computation matrix, precision recall, and then also the trade-off between precision and recall. So when we change the threshold, we can get the ROC curve and also calculate the error under the curve. So yeah, this is a part of like the introduction part to today's algorithm, and I hope it's kind of useful. So for the next algorithm, it's a k-nearest raised label. So for this algorithm, it's not trying to learn a model, but it will just based on the current existing samples, we make predictions based on the current instance. So for example, if you have this new example coming in, you are trying to calculate the distance between this new sample to the nearest labels. So the k means, okay, we restrict to the nearest k neighbors. For example, here we just pick out the 3, k equals to 3. We pick out the 3 nearest labels, and we do a majority vote. Like we simply calculate what's the proportion of each class among this k nearest label. So we will pick out the most, like the most predominant, the most majority as the predicted class. So this is a very intuitive algorithm to do, and it's also like what we did in our real life, right? So we hang out with friends, and those friends should share a lot of similarities of us, like the same hobbies or same like same taste. And maybe same personality or something. So it's a very intuitive way to do the machine learning. So yeah, I think it's kind of like a very intuitive thinking, and it works pretty well in many cases. So when we see this KNN will predominantly based on the distance. So we calculate the distance between other samples, and then we guess what's the class this new instance is. So the distance can be a tricky thing to do because we have a lot of distance metrics. For example, the most used one is the Euclidean distance. So which is just simply like you have a vector of length n, like different coordinates. You simply calculate the difference and then take a square, calculate the sum, and then you take the square root. So this is also called L2 norm. So L2 norm distance. And also there is another Manhattan distance, which is not the take the square and then take the root, but we take the absolute value. So it's more like the Manhattan street, like you go from this block to another block, you need to go straight and then take the left or take the right. So it's more like the it's more like a street, a Manhattan street scene. So this is called the L1 norm of distance. And there is a generalized version of distance for example, Euclidean distance or Manhattan distance can be summarized into this Minkowski distance, which is also denoted as LP. So basically you can think, okay, we take the P equals to 1, it's Manhattan distance. If we take the P equals to 2, then it's a Euclidean distance. And the P can be any other things, like can be a infinity. So this will becomes a Chebyshev distance. So yeah, from here, I just want to mention we have a lot of distance measures. And usually in the biology field, we usually stick with Euclidean distance. Like we calculate the genetic distance between an individual to a population. So we basically take the genetic Euclidean distance of the genotypes. The third one is called the naive Bayes. So if you take some stats course, you probably know the Bayesian theorem, which is the mostly based on the posterior, the conditional probability formula that the posterior equals the likelihood times the prior and divided by a normalizing constant. So the posterior, in our case, will be, okay, when we observe this X, what's the probability of each class, right? So this is called the posterior, and it can be written as this, like proportional to the likelihood and times the prior of this class. So if we assume that the features like x1 to xn is independent from each other, so we can factorize this likelihood out to be like a px1 conditional on class 1, a specific class, and a p times px2 condition on a specific class, and then times just writing this joint probability to be a factorization probability. So this will give us the final posterior probability if we normalize them to be 1. So here is a question: why naive Bayes is called naive? So actually, I just mentioned that they have an independence assumption. They think the features are independent with each other, condition on class. So this is so-called naive. Although this independence assumption doesn't necessarily hold in many cases, but the naive Bayes algorithm sometimes perform pretty well. And because they only require like the number of class and also the number of features, so the computation is usually very fast. Yeah, so yeah, I give the answer that we make this conditional independence assumption. So this is why they call the naive Bayes. So when X is a continuous variable, we usually assume to be a Gaussian naive Bayes. So basically, Y here is equals to is equivalent to C. So those are the same thing. So we will assume that for the mean of this cluster, the probability of a given feature will have this Gaussian distribution. So when we have this thing, we can write the above formula to be more solvable format. Basically, when we write this thing, we want to maximize the above formula, and then we simply take the log, right? And then we take the sum. When we are in the log space, the product can be written as the sum, and then you just try to maximize the sum of different marginal distributions. And so we want to maximize something. So basically, we want to minimize the negative of log likelihood. So this is still, we can write the loss function in the negative log likelihood form. And the algorithm, they have a goal. We want to minimize this object function, so they can estimate the parameters well, and then they will give you an answer about whether this class, after training, they can give you an answer about what's the most likely class this instance come from. Yeah, so yeah, I think it's a quite statistical language. So I hope you just kind of like get a sense of what I'm saying. So we have covered 3 different algorithms. The fourth one is the support vector machine. So I don't know if you guys have heard about it before. The support vector machine is a very classic and also a very powerful algorithm to do the classification. So here we can, for example, if we have 2 classes of data points, and we want to draw a line to separate those 2 clusters. For example, we can draw H1, H2, and H3. But basically, we want to separate those 2 clusters, they should be located on the 2 sides of the line. So if we want to achieve this, which line do you think is the best option to go? Like if we want to train this classifier, simply by drawing a line, which line do you think we should go for? I think this one is easy. We have the third one. Yeah, that's correct. So so here the reason why we choose the third one is that so first H1 cannot finish the separation well, because it's like cannot separate those 2 clusters. They go through 1 cluster. And H2, although they can separate the clusters, but the distance between the smallest distance between the clusters, the cluster 1 or the cluster 2 is smaller than the distance to the H3. So H3 separates the clusters the best. So we think H3 should be the one, because when we have a new instance come in, they're always with some randomness. We want this model to generalize well to new things. So we want the margin to be as far as possible. So like the difference as near as possible. So the decision function, if we draw this line, can be written as this. So basically, if a cluster, they located below this line. So as we know, if it's a 2-dimensional thing, so this line can be written as a linear combination of x and plus some intercept. So if it's below, then this thing will be smaller than 0. So this part will be assigned with 0. And on the contrary, this part above the line will be greater than 0 and they assigned with another label. And this is for 2-dimensional case. If it's more higher dimensional, so those H3 will not be a line, but be a plane. For example, if it's 3-dimensional, it's a plane trying to separate the space into 2 parts. And if it's more than 3-dimensional, so it's called the hyperplane. So it's like, I think a human brain probably cannot imagine that, but it's like something like generalized from 3 dimensions to 4 dimensions, hyperplane thing. So as we have said, the H3 is a line we want to go for, but we want to write it in a more mathematical formula so that we can transform into an optimization problem, then the computer can solve it. So here, as we said, H3 is the best because they can separate the cluster well, and then they can maximize the margin. So for example, those two dots, only this red line can have the biggest distance to those two dots. So this is so-called the large margin classification, and it's related to the omega, which is the parameter before the x. So it's 2 divided by the L2 norm of omega, or W in this case. So we want to maximize this margin, which is just trying to minimize the W, right? Because this is in the numerator part. We want to maximize this whole thing. It's just trying to minimize this part. So here, it's what we try to achieve, that we want to minimize this this function, but we have this condition that we want the dots to be well separated, like the or located from one side of the line or from another side of the line. So this is a constrained optimization problem. So using some quadratic programming techniques, we can actually solve this optimization problem because these are proven to be a convex optimization problem, which is easy to solve. So using this, we can actually know that why this method is called the support vector machine. So basically, only the dots on the margin will determine the decision boundary. Like if you have a new dot located here, those dots will not influence the boundary decision. So this margin, these vectors, these dots on the margin is called the support vectors. So yeah, I think this is something not everybody knows. So you can probably one day talk to your lab members. Okay, you don't know why support vector machine is called support vector machine. So this is why. Yeah. So adding more training instance outside of the street, if we think this is a street, will not influence the decision boundary at all. So this actually have an advantage during the testing. So basically, when we finish the training, only the support vectors can be useful for making the decisions. So that means not all dots is involved in the prediction. Only a small part of the dots involved in the prediction. So the above part is the ideal case that all the dots are well separated. But there are some cases that, okay, if we have a green dot in the blue population, or if we have the blue dot in the green population. So in this case, the drawing a line to separate everything well is impossible, right? Because we cannot find a line or a plane to somehow drag this dot back to its cluster. So this is a so-called soft margin classification that we allow some violations, which is shown here. So the distance, like this dot to its original clusters distance, support vectors distance, is added as a penalization term, so that we want to minimize this part, but we allow some kind of violation, but this violation cannot be too big. So this is why we minimize the whole thing, right? We want to minimize this part as well as this part. And the C here is just a hyperparameter. So basically, if you want to allow for more violation, then you probably have a very small value of C. But if you are really really clear about the violation, you give it the other directions. So this is the so-called the soft margin classification. And all about the previous part is the linear case. Like we want to find a line to separate things well. We want to find a plane to separate things well. So basically, those are just a linear combination of axes. But sometimes we want some nonlinearity. So for example, in this case, we cannot draw a line to separate the triangle from the square because the square scattered like at two ends. The triangle is in the middle. So we cannot do it with only a line to separate things. But we can actually add one more feature. For example, at x2 equals to x1 squared. So basically, in this case, it's more like a polynomial kernel, like a mathematical calculation. So in this new space, we can draw a line to separate the square from the triangle. And sometimes we also have this similarity measure, which is trying to use a similarity calculation. Here it's called the Gaussian radius basis function, RBF. And here is the formula. So basically, it will calculate the new instance. For example, some instance here, like the leftmost blue square at X, and the L is a landmark, which is, for example, like the density mean, like the showing at the red dot. So we want to calculate the similarities between this distance and the landmark. And with this exponential negative gamma. And here, gamma is also another hyperparameter. And this formula will give us the value between 0 and 1, right? So we have we have 1 when this whole thing equals to 0. And otherwise, we will always smaller than 1, but always greater than 0. So this will somehow try to, okay, if this distance is far from the landmark, then we have a very small value. But if it's very close, then we will have a high value. So in this case, we can actually transform the left part to the right part, that we can still like using this x3 as another, like what we calculated from this similarity measure in this plot. We can well separate the green triangle from the blue square. So yeah, this is just like a 2 kernel tricks that you probably will face when you run the SVM. Like there are some parameters to train to hyperparameters to train about. And I think we can take a 2-minute break, and then we continue to learn the decision trees. So welcome back. I hope the past few algorithms is informative, that you actually think it's reasonable that they can do a good job in the classification. So next, we will learn this decision tree, and here it's a very, a very intuitive algorithm, a white box algorithm, usually we say, because it's very easy to interpret. So it's more like we make decisions in our real life. For example, if I want to buy something, I will need to compare like from a particular product to the rest, and we compare it from different features. For example, if it's expensive, then if it is, then I will just, okay, I'm not going to buy it. So it's more very similar to the decision-making process. So this is called the decision tree, that every time we will split our data, our candidate, into 2 parts. based on one feature according to a threshold. So here it's actually the algorithm that we are going to do. That is searches for a feature K as threshold T that produce the purest subset. So the purest is like, okay, we have the class label. For example, if we split the data into two parts, and we want one of the cluster to be like more homogeneous. So this is so-called the purest. So the cost function is writing at this. So we have this J, K, and TK. K means the case feature. TK is the threshold T at the feature K. So we have this M over M left, G left, plus M right divided by M G right. So this G is actually a purity measure called Gini index. So it's initially a measurement for the wealth distribution, like 20% of people in the world takes 80% of money, so something like that. So it's a good index to measure the inequality. And here we actually use them in the classification part. So we want this cluster to be as pure as possible. So that means we want G to be as small, like close to zero, close to zero. And this is then we will be happy. So in summarize, we will need to take into consideration the balance, like the ratio of the samples, and also the Gini index. In this example, we actually can write. So the left part is a tree structure. We actually can interpret it into a region division. So basically, for example, for this first cluster, we can clearly see this cluster is deviate from the rest of the samples. So here is like for the very beginning of the tree, which is depth 0, we will have this threshold at this particular petal length feature. And then at this part, we will divide the data into two parts, and we clearly see this division is reasonable. We divide a particular subset, which is very pure. And then we move on to do another kind of division, which is based on the petal wise. So we still try to find the threshold, and then this threshold can give us as pure cluster as possible. For example, we find this threshold here, and although we cannot achieve the 100% purity, but this threshold is good enough that and it's better than we draw a threshold from here. So this kind of decision tree is it's very intuitive, very interpretable. Like if we run like a machine learning algorithm like random forest or neural network, usually we don't know why the machine can make such decision. But this type of algorithm, like decision tree, can actually make things very transparent to us. So this is something we like, because we want to understand what's the reason they make this decision. But there is a problem for the decision tree most of the time. So it's kind of unstable to some small variation. So basically the left part and the right part, basically the data doesn't show that much kind of difference, right? Only a small difference maybe at some of the samples, but the division is it's very different. For example, here they try to separate the three clusters purely based on one variable, but at two different thresholds. So although the dots distribution is kind of similar to the left, but the region division is totally different. So this decision tree, although it's very powerful, but yeah, it suffers from some limitations. So later, the machine learning people, they came up with some more advanced learning framework. So I think this part is the most interesting part for today's workshop, because it's actually you can actually see some intellectual spark of human species. So for example, the ensemble learning is actually very similar to, okay, we need to discuss something with with many people so that we don't make mistakes. So this is the so-called the wisdom of the crowd. So that means, okay, if your classifier is a weak learner, that means your classifier is not perfect. It makes only a very slight improvement than random guess. But if you consider you have like several hundred of these weak learners, you can still train a strong learner. And this strong learner is actually can perform well or even better than the best individual learner. So this is the so-called ensemble learning. And the ensemble learning, as we said, the wisdom of the cloud should be as diverse as possible. If the cloud is just a replication of one individual, so basically the wisdom cloud will just be the wisdom of an individual that will lose the power of ensemble framework. So for example, in this figure, we have several weak learner logistic regression. The first thing we learn, the SVM classifier, or some other algorithms. And each of them, we train it on the data, and then we have a classifier. But although the classifier may perform bad or don't have that reasonable performance, but if there is a new instance come in, we can try to run this new instance with each of the classifier, and then take the majority vote. Like they have like a vote, and we collect their opinions and then find them the most common conclusion. So this kind of conclusion is our final decisions. So this is called the ensemble, right? We listen to all the opinions and then select the best one. So following this ensemble learning framework, we can actually try to improve the decision tree. So as we see, decision tree has some problem, like they are very sensitive to the small variations, but we can try to do an ensemble of decision trees. This is so-called random forest. So yeah, I think the name is very informative itself. The forest has a lot of trees, so this is so-called the random forest. And the randomness comes from, okay, we have this training data, a lot of samples, a lot of features, but each time we only select a subset of the samples, and also select a subset of the features. So this will give us a classifier. For the next one, we select a different subset of samples and features, give us a different classifier. If we do this part at for example, we train 500 decision trees, then we will have 500 different classifiers. They probably will give different results. So it's very diverse. But after we do the training, and we have a new instance, we can also use the crowd of wisdom, like the ensemble majority voting, to get the final vote. So this the advantage of doing this is that we can actually reduce the variance of a single tree. So the variance of a single tree means, okay, it's very sensitive to some small variations, and if a new sample comes in, it probably give it better results because it cannot generalize that well to the new sample. But if we have this random forest setting, they usually perform pretty well. We will later see in our Jupyter notebook task compared to the decision tree, random forest actually improves a lot. And we also, because we do this subsetting of the features, we can actually try to estimate the feature importance. So this is sometimes very important for our biology people because, for example, we have so many genes. We want to know what particular gene is the most interesting gene that they drive to a specific phenotype or they play a specific role in some process that we that leads to the results. So this feature importance is actually can be calculated in this source that we want to know the feature. If we use a feature, how much impurity we can reduce on average across all the trees. So that means okay, with this feature or without this feature, what's the difference? It's more like sometimes more like the biology experiment, right? We knock down some genes and then we know what's the difference. So this is the kind of have a comparison. So this whole part is called the, sometimes we call it as a bagging, like a bootstrap aggregation. So it's a very short name for bagging. For bagging. There is another thing called boosting that we can combine the weak learners to form a strong learner. So this is kind of different from the previous one because this is done in parallel. Like we train different trees and then aggregate them into like by majority voting into the final decision. But this one is trying to, okay, we can train the predictors sequentially. Like each time we train this model and we maybe evaluate it on some predictions, and then we found, okay, what kind of cases this model didn't do well. So then we can guide the second model to maybe they can learn well in these particular cases, and then still make new predictions and so on. So this is kind of like try to correct the previous mistakes in a sequential way, in an evolutionary way. So one example is called the AdaBoost, so which is short for adaptive boost. So adaptive boost is trying to ask the model, ask the algorithm to pay more attention to the training instance that the previous classifier didn't perform well. For example, we have this original data set. We can train this decision tree algorithm, and we misclassify some of the samples. Then for the next generation of classifier, we will ask the model to maybe they should focus more on these misclassified samples, and then do another round of training. And then we again get a new set of misclassified samples. And then we repeat this process to train a lot of classifiers. And then later we will combine everything together. For example, here we have 3. If we just overlap all the 3 region divisions, and then we can actually say, okay, this algorithm can separate the whole space into some subsets. So yeah, this is kind of like I think it's a very smart idea. Yeah, also the random forest is a very smart idea that it can try to correct things that you make mistake before. So it has some kind of human learning flavor, because when we do some learning, when we write exercise, we make mistakes on one thing, so we go back, correct, and then move on. So this is some interesting ideas here behind. But one thing is that how should we tell the algorithm to focus on the training instance they didn't do well? We cannot tell the algorithm, oh, hey, can you pay more attention for those class instance or cases? Yeah, the algorithm itself cannot understand our human language, right? So we do this by putting some weight to each of the instance. For example, we initialize every instance at the very beginning. We initialize with equal weights, and then we train a predictor like the decision tree. So for this particular classifier, we will have a weighted error rate. That is for those cases that they didn't do well, the predicted value and the true value, they are not equal. We will have this error rate calculated, and then we will calculate the predictors weight. So this is simply the original error rate in this formula, and the eta here is the learning rate. So for each of the predictor, we have the alpha j, and then we will weight. We will update the weight for each instance. For example, if this instance is correct, then we remain the same. You don't need to you don't need to focus on this instance. But if it's wrong, then we will have this exponential alpha j, which will increase the original weight to some level. So this will give us a new weight, and then we take the normalize, try to make the weight, the sum of weight equals to 0. So this new weight can for those misclassified samples, they have a higher weight among all the instances. So this is how we assign. Okay, you should pay more attention to the misclassified cases. So this is how we achieve this thing. So we repeated the whole reweighting scheme until we reach to the design the number of predictors. For example, we design 500 predictors to do the prediction. Then we will stop when we have 500 predictors, or we have a very perfect predictor that separate everything well. So this means, okay, we don't need another predictor. We already have the best. So after we finish the training, we can make predictions, simply run all the predictors and then calculate the weighted average. So the weight is the alpha j for each predictor. And another boosting algorithm is called the gradient boosting. So previous for the adaptive boosting is trying to find update the weight for the instance. But this gradient boosting is trying to predict a new model from the residual errors. The residual errors, you can think it's just like the cases that we didn't do well. So this part is somehow very similar to the previous one, but using a different scheme. For example, we will fit the function fm equals the previous one, like the previous generation of a classifier, plus newly learned, like this function is learned from the residual error. So we make up the errors based on the previous one, and then we learn new thing. So this will tends to give us more accurate results. So still, this one is like the loss function across generations. We will minimize the loss functions. This is more about the boosting algorithm, and we have this last part about neural network. So probably you have heard about it all the time. So when we talk about neural network, we actually mean we have a much more layer of artificial neurons, and they are connected with each other. So they jointly looks like a neuron thing in our brain. So one interesting thing is that logistic regression, the very simple one we talked at the beginning of the workshop, actually can be regarded as a single layer of neural network with a sigmoid activation function. So neural network, on the other hand, can be regarded as multiple layers of logistic regression, but they have different activation functions. So for each layer, for each cell in the neural network, we can find some similarities to the neurons in biology. So for example, in biology, we have these dendritic branches. So they receive the signal from other cells, like maybe many other cells. And then they, after they are activated, like they fired, then the signal will transduct to the next neuron. So which is very similar here. Like we receive signal from all other neurons, and then we will activate. If we activate, we transduct the signal to the next layer. So it's very similar to the biology. And for the activation function, we actually have a lot of choice. So, but somehow in reality, we usually think the ReLU, like the rectified linear unit, is usually a good default. And if there is no activation function, what actually will happen? Have you heard about this thing before? So basically, if we don't have an activation function, so we can think, okay, this one is a linear combination for the other ones, right? And then this one will be a linear combination of the middle ones. So because we know the linear combination of a linear combination is still a linear combination. So that means the middle ones is not important. So basically, it's just equivalent. The output is a linear combination of the input, which is the linear regression. So if there is no activation function, the neural network can be reduced to a linear regression, which has a very weak learning ability. So because linear regression, we know it's a very primary tool. And if we want to learn some more complicated function form, we should have this activation. So as I said, the ReLU is a good default, and here is what actually ReLU did. It's like it equals to 0 when the x is smaller than 0, and it will be equals to x when x is greater than 0. So yeah, it's a very simple math formula, but it's very effective, very powerful. And the good thing for ReLU is that it's very convenient to compute, especially when we're doing the neural network. We need to calculate the derivative things, and the ReLU is a good activation function that compute very fast, and also it has some kind of similarity to biology in the neuron spike sense. For example, we during the resting state, the neuron have some kind of potential. When they receive stimuli to some threshold, they will be fired. So we can actually see the similarity from this part to this part. Right? It's a quite interesting observation that the well-performed activation function actually have some kind of biology similarities. And there are also some other functions like sigmoid or leaky ReLU, which is also used in the maybe the computer vision field, and people are inventing more and more activation functions. But those things I think we don't need to worry about right now. UNE renewal is good enough for most of the cases. So here, I would like to using this video or give image to show what is actually neural network doing. So basically, let me see. Yeah, basically, we have an image, right? So basically, it's a 28 by 28 dimension. So if we span it into a vector, and then we create this neural network with hidden layers and also output. So for each layer, we have the value, which is the pixels and the weight. And then for the output layer, we will have 10 digit, which denotes to 0 to 9. So basically the 10 digits, since this is our output. We use a forward propagation that tries to compute the loss functions. So basically with the current weight, current input, we can make a prediction and compare the prediction to the true label. We can calculate the cross entropy loss. And later, after we have this entropy loss, we can actually compute the derivative with respect to the weight. And this will give us a gradient. So with the gradient work, we actually can, we know that following the direction of gradient, the decrease is the most fast. So this is how we do the weight update. That is, we use the original weight minus a learning rate times the derivative. So at the new weight. So by doing this, we actually try to make the loss smaller and smaller. So which is showing like this figure that from the loss or the cost function, which is very high. After we update the weight, we actually go slower and lower. So this is showing when we minimize the loss, we actually make our output more similar to the real labels. So this is a so-called a learning process. So here, the forward propagation, we're trying to get the loss, and the back propagation, we're trying to update the weight, and we do it iteratively. So then the loss is minimizing again and again to until we reach to a local minimum. So I think that's all about the algorithm for today. We actually can summarize them into a table that we have the logistic regression, KNN, naive Bayesian, and the support vector machine, decision tree, random forest. I didn't put the neural network here because the training time or complexity is highly dependent on the architecture of neural network. So they have different advantages or limitations. For example, logistic regression, we know it's very simple, it's easy to interpret, and also it requires very few computation, and also can do some kind of fancy stochastic gradient descent when doing the learning. But it has some limitations. For example, it cannot handle the nonlinear problem. For example, we look at the support vector machine, there is some kind of candle tricks in support vector machine to handle nonlinear case, but logistic regression cannot do that. And because it's a regression problem, so it's also sensitive to the outliers. And when we have a very huge feature set, it tends to overfit the data. So we need some regularization. And KNN is very intuitive and easy to implement. And because these don't have any assumption about the underlying data, it's actually a non-parametric method can be adapted to many cases. but it has some limitation for the slow speed, especially when your data is very big. You need to compute your instance with every instance in the data set to find the nearest neighbors. So you actually face a lot of computation. And it also don't perform well in the imbalanced data set. For example, you have 90% of sample belongs to one class, and only 10% of sample belongs to another. And when the dimension is very high, the distance will also have some problem. You probably cannot find a trustworthy nearest neighbor. And also it may be sensitive to the outliers. Naive-Bayes is very computational efficient, but the limitation is they have this independence assumption, the conditional independence assumption. The support web machine is very powerful, like they can handle the linear, nonlinear problem, and they can generalize well in practice. So in many cases, SVM is usually performs well, but consider the training time is n squared. So like it cannot easily scale up to a very huge data set. So this is a limitation. And decision tree advantage is that it's very easy to interpret, very intuitive. And they require little data preparation. So we don't need to do any kind of transformation like data feature scaling things. It's very very easy to train, or sometimes easy to run. And also it scale up to well to the large data set because it's a tree structure. So the complexity is no longer n squared, but n times not n. But it's kind of not robust to the small variation as we have seen in the past slides. And also it may have the problem of overfitting. For the random forest, it's a very interesting idea or ingenious idea that it can reduce overfitting by getting more and more opinions from some weak learners. It also improve the accuracy, and they also have the built-in vision importance. But the limitation probably is just like the black box algorithm, and also compared to the decision tree, it trains a lot of trees, so it will somehow require a little more training time. So I think that's more about theory for today, and I think probably we can do some practice, and then we can take some break. So if you don't understand the whole some part of the workshop, especially for the algorithm part, still don't worry about it, because recently the package is well developed, and usually you can just import one, like using 3 lines of code. You don't need to bother with the details. But the workshops, I still think it's important to introduce those algorithms so that you learn, you know what you are dealing with. Otherwise, you just import something, then you're not going to understand what's going on here. So for the Jupyter notebook, we can still go to the QC Bio machine learning with Python, and you can try GitHub pool, or if you haven't do it, it will like GitHub pool try to fetch the day2 folder into your folder. Because I already done that, so it is set already up to date. So after you try that, you can enter into the day2 folder, and then you try to run the Jupyter notebook. And yeah, so from the day2 folder, we have a lot of files. Just open the day2 notebook, and you can see the contents. So after you finish that, you can take a look at the table of contents, which is actually the covers almost of the algorithms we talk about today. So for the very first thing is that we try to, so basically this workshop, Jupyter Notebook is trying to run those classifiers and also explore some interesting topics. For example, try with how to do the hyperparameter tuning. And also we can actually see some underfitting or fitting issue in some of the examples. So first we just import all the packages we have. And then we know the data. So yesterday we trained a very simple decision tree on the breast cancer data set on sklearn. And still today, for the first computation task, we're also working on this breast cancer. So we first load the breast cancer data, and then try to check the breast cancer data structure. So basically, you can directly print what's inside the B cancer data structure. You can see a data packet. So those are two things we care about. One is the feature, one is the label. And for the feature, we can check out the dimension by using this shape attribute. So you put the dot shape, it will tell you we have 569 samples. Each sample has 30 features. So this is what does the data look like. And yesterday, we trained a classifier purely on the whole data set. So as I said, those are not ideal because we get a very small, we get a very high accuracy, but we cannot tell whether those models are trying to overfit the data or not. So today, we are going to split the data into training and testing. So the training data, as I said, is purely used for machine learning model development, and the tested data should never be seen by those models during training. So those are just used to evaluate model at the very end. So after you do every training, parameter changing, and then finish everything, you then move on to the test set to get the estimate for generalization error. So here we can, for example, we can write a for loop to iterate each sample and then divide them into training and testing. But here, I think we can just make our life easier using this train test split provided by sklearn. Specifically in the model selection part, you import this function and then run this line of code. Remember that we can set the test size to be 20% or some other 30%, some other percent unite. And here we notice there is a random state 22. So basically this number is not that meaningful, but when we try to set the random state, that means we split the data. In a fixed way, because when we do the data splitting, we actually do it randomly. And if you set this seed, it will become reproducible. Like whenever you open the notebook, run this chunk of code, the train and the test will always be the set of data you tried previously. So this is just for the reproducibility purpose. So after you do that, you can again check the shape of your training and testing. So here we have 100 around 100 for testing and 450 for training. So our goal is to train a classifier that use X to predict Y. And here for the for each of the training and the testing, we also notice the data set is imbalanced. So basically you can try this NumPy unique. And with this Y train, with return count equals to 2. So it will return how many zeros and how many ones in your data set. So we can see that those are not equal. So which means the data set is imbalanced. And for the meaning of the 0 and 1, 0 means the malignant tumor, and 1 means the benign tumor. So for part 1, we also want to mention that for the sklearn design, that its API is remarkably well designed. If you want to check out the design principle, you can go to this link. And for the well designed, because it's consistent across all the objects. For example, you try to create a logistic regressor. You try to train a random forest. They will share the same syntax, which makes the training very easy. You simply just try to fit your model, try to create an object and then run the fit method. Input your training data and the training label, and it will finish the training for what the classifier you choose. And they also have some transformer, which means you do some data transformation and predictors that when you have the model you want to predict on the test data set, this will return the labels, the predicted labels. And also the object can allow you to inspect some of the, for example, the parameters or some of the methods. So any hyperparameter can be accessed just using a dot and also the hyperparameter's name. And all the estimators learned parameters will be accessed still using the public instance, but they will carry underlying score at the suffix. So later we will see that. And also what the data is provided with a NumPy or SciPy matrix. So this means it's very compatible with other packages. If you know how to use the NumPy, you can directly apply those techniques on the data. And so there is also a very useful command or the module called a pipeline that you can actually state, for example, some data transformation steps into a single pipeline. And then every time you have a new data or different set of data, you simply run the pipeline. So it's very flexible and also compact. And it also provides a very sensible default. So even though you don't specify any other parameters, the default parameters usually works pretty well in the training or in the testing. And it's also very user friendly. So if we go to the website, we can actually see there are 6 sections: like classification, regression, clustering, dimension reduction, model selection, pre-processing. So for example, for clustering, if I want to know what is, for example, the decision tree, it will have some explanation figure and also some code. So I think for most of the time, if you want to train some algorithm, just go to the website and try to follow the code and then reproduce it on your own. So you probably will end up with good results. Right. Yeah, so it's very well documented. So next, we are going to do some simple training. For example, classification. So maybe we can just go over this example and then we take a 10-minute break. So for example, for the first thing is that we from Skinner linear model import logistic regression. So this will have a function, and then we create a new model called a log-reg logistic regression. So this will give us a regressor, and then we call the fit method, which will when we input the X train, Y train, it can do the training very soon. And then we just do the predict, so that we can get the predict label. If we so here I just try to see what's the fitting look like. So I input the X train to let it predict, and for the testing part, I assigned it to the Y pred. So let's see, for Y pred, it will generate the predict labels. And for the performance measure, as we said, there is a confusion matrix we can use, and very easily we can import this confusion matrix method or function from a Skinner matrix, and just run it. So we can see that most of the class are predicted to be accurate. For example, if it's 0, then it's predicted at 0. If it's 1, it's predicted to be 1. So this is for the training and for the testing. And we actually can visualize the whole thing using this confusion matrix display, like showing the corrected predicted. If it's 0 and 0 is correct. So the accuracy we can see is usually very high, just using a logistic regressor. So I think probably we can take a break from here. We will resume after 2 minutes. And we have using this computing matrix display to display the results on the test data. So we also in today's workshop, we also introduced the accuracy, precision recall, F1 score such measure. So luckily, you don't need to calculate those things by using the formula. Specifically for the sklearn, it provides these options for you. So simply, it's just you input your predicted label and your actual label, like real label, then it will return out value for you. So from here, we can see the accuracy, precision recall is usually pretty good for the logistic regression, which means the features is meaningful, and we actually dealing with a kind of a simple or easy classification problem. So in the workshop today, we, in addition to the numerical measure, we also talk about the ROC curve, like a precision recall ROC curve or traditional ROC curve. So for the ROC curve, we are not satisfied with just getting a value. Instead, we want to change the threshold and then see how the precision recall changes. So in such context, we need to have a continuous score or probability that can allow us to change the threshold. Yeah, if you just input like a prediction, which is 0 or 1, there is no threshold thing. But if you input the probability to be 1, then you can, by changing the probability threshold, you get a different precision recall. So for the logistic regression, you can simply call the predict probe, so which will return a NumPy array, and for each sample, it will contain 2 values. One value is for the probability being 0, and one value for probability being 1. And for the ROC calculation, still the sklearn help us to calculate it very easily. For example, we can just run ROC curve with the probability and also with the true label. Then it will output the false positive rate, true positive rate, and the threshold. And if we want to calculate the area under curve AUC, we just use ROC AUC score and still include the label and the score. And the following is just some code that try to display the plots. For example, we plot this FPR, false positive rate, against the true positive rate. And then we add some dashed line, which denotes to the random guess with different X and Y label with the text showing what's the AUC. So here is what we have for the ROC curve. Precision record ROC curve is similar. We simply replace the ROC curve with the precision record curve and calculate the average precision score. So which is the definition as showing here. The following is similar. We just simply plot it out. So here we can run those two results, like ROC curve and the precision record curve. So as we see here, logistic regression achieves AUC to be 0.98, which is pretty high. And we see that this is like if you are going to train a classifier in your project, you see this AUC, probably this is something good, good to you. And besides the plot we make, like we wrote two functions to do that. ROC curve, the sknN can also provide some function to generate the ROC curve. So for example, here, still we run the ROC curve to generate false positive rate, true positive rate, and then we can simply call the ROC curve display. By inputting those variables, it will generate a figure like this. But the limitation is that it allows self-editing, like you cannot customize the plot the way you want. So I would suggest to stick with the writing a plot function yourself and use it again and again. So the first classifier is logistic regression, and which is very simple to use. And maybe it's a time that probably you can try, for example, check the documentation and then write the code for the support vector machine. So I will give you maybe two minutes for this. So I will just release the answer. Well, it's just very similar to the previous logistic regression. We simply from SVN input SVC, which stands for support vector classifier, try to initiate a model and then try to fit the training data. So after that, we can run the SVM classifier decision function to get the Y scores. So after that, we can also plot the ROC curve and the PR ROC curve. So it's slightly better than the logistic regression, because we know like logistic regression is very simple. SVM is need more complicated advanced technique, so it's capable to handle more complicated situation. So the third one is naive Bayes. So we from sknN naive Bayes import the Gaussian naive Bayes. Following the same tutorial or same procedure, initiate the model, fit the fit the training data, and then we predict the probability on the test data, so that we get the scores. So this is what we said, that SK9 is very consistent no matter what your classifier is, naive Bayes or logistic regression or SVM. It will always have the same syntax. So it's very easy to use. Once you master one, it's very easy to extend it to others. So here, we also plot the ROC curve. It's 0.891. So kind of like more slightly better than the SVM. It's kind of surprising that although it has those assumptions, the conditional independence assumption, but the naive Bayes still perform pretty well here. So probably this means the 30 features we have is somehow is exclusive from each other, or yeah. But anyway, the prediction results is very good. For the k-nearest risk label, we import the k-label classifier, and we set the number of labels to be 30. So this value is manually defined by me. So you can probably change whatever values you like. So this is actually a hyperparameter we will need to consider to optimize. For example, whether we choose 50 or 25, the results probably get changed. So here we just fix it as 30 and then train on the training data, and then predict the probability on the test data. Again, we plot the ROC, the AUC ROC. The AUC is 0.9875, so it's still a very high value. So lastly, next we tried the tree-based method from the SK9 tree import decision tree classifier. So here we set the max depth to be 2, like the depth of the tree depth is 2, and then we feed the data. And the max depth is also a hyperparameter we can optimize. After that, we predict probability on the test data. So still, like from all the training and the testing, all the classifiers, you should notice that we only use the test to predict the probability and then compare. So it's the evaluated model. The test should never be involved in the training. So always remember this, don't confuse training, testing, or misalign them. Yeah, so after we training, we see the performance is less better. So probably you change maybe different hyperparameter, the performance can increase. But right now, if we just fix to be max depth to be 2, we get 0.94. So which is like the smallest among all the classifier we have tried. But later, if we compare it with a random forest, like we import random forest classifier, we also use the same tree depth as 2. And this time, we allow the number of estimators, like how many trees we are going to grow in this forest, to be 500. And then we fit the data on training data, and then evaluate on the test data. So this time, surprisingly, we can achieve 0.993, which is by far the highest. And also compare random forest to the decision tree. Although the hyperparameter for max depth is the same, but we can clearly see there is a 0.05 AUC increase, which is kind of like very exciting that this random forest is actually doing well compared to others. So here is a question. Actually, we just solved that. Using random forest, we train a lot of decision trees. After we averaging all the decision trees, like we ensemble every decision tree, we can actually outperform a single decision tree. So this is a secret for this is the reason the K, Y of random forest works better. So next we try the boosting. So here is a method called XGBoost, which stands for the extreme gradient boost. And this method is actually like invented very recently, like after 2010, and this is invented by some PhD student in University of Washington at the time. Now he is an assistant professor at CMU. So this XGBoost is kind of like a very useful tool for the regression for the classification. It outperforms many classic machine learning algorithms. So, but this XGBoost is not a part of the sklearn. You need to install it by yourself. So after that, we import XGBoost at XGB, try a classifier. And because we have a binary label, like a 0 or 1, so it's a binary logistic. And then, but although this XGBoost and sklearn are two different packages, but they share a lot of similarities in the context. So for example, if we want to train it, we still using the fit method. After that, we evaluate on the test. So here, this one gives 0.998, which is still by far the highest. Random forest is a little worse than XGBoost, but they are like all of them approach 0.99. So lastly, we can take a small bite on the neural network. So this is something new, and also sklearn, although they have some multi-layer perceptron module, but if you want to make your life easier, probably you should try the Keras, which is very easy to use. They have a very good API and also very good documentation. So you can simply run this to install the TensorFlow and Keras. TensorFlow probably will be a little slower to install because it's very huge, around 200 megabytes. But TensorFlow, it's a very useful tool in deep learning field, especially you are working on the computer vision, you are dealing with some robot things. The TensorFlow is pretty important in those fields. So after we install, we can from TensorFlow import Keras, and we will try to build a machine learning. We try to build a neural network from this Keras. So first we use the Keras models sequential. Sequential is a very simple kind of model in Keras, which just means okay, you stake each layer sequentially and connect them sequentially. So it's just what we use to create the structure. And then for each layer, you add them. For example, for the first layer, because we have 30 features, we need a flattened layer that we have 30 nodes. And for the second one, here I just use a manually designed 16 neuron layer, and this neuron layer are fully connected to the previous layer, and they use a relu activation. For the last one, because we only have one output, like whether it's 0 or it's 1, so the output will be one single neuron. So I set the dense number of neurons is 1, and the activation is sigmoid. This is because we output either 0 or 1, so sigmoid is the obvious choice. So this is like actually the framework for this neural network. We have 30 input neurons, and then we have 16 hidden layer neuron, and then finally we have this one single output neuron. So each of the edge here is a collection, a weight that each node in the hidden is a linear combination of the input neurons. And with the activation function, it will outperform the value, and also with some weight to the final layer, which is the output layer. And the output layer is also a simple linear combination of the output of the hidden layer, and they will be transformed by a sigmoid function, give a value from 0 to 1. So you can check the model's layers by this layers attribute. If you run it, it will show okay, what's in this model. And if you want to build this model, so first we just specify the architecture. If you want to make it a model, you simply run this build method. And if you want to check, for example, get a statistics summary about this model, you can run this summary method. So this will tell you this model is a sequential model, and it will output the number of layers, and also output the number of parameters in each layer. So after that, we see this simple, very simple neural network architecture actually contains 513 parameters. So this is actually bigger than our samples, right? We only have 400 and around 400 samples for training, but the parameter we have 500. So this will lead to some problem. Maybe the model is not it is overfitting the data, or the model will not learn the data well. So based on this, we face an issue that data is not enough. But anyway, we can continue to run it. So before that, we actually can access each layer, like from the layer attribute. And for example, if we want to access a second layer, we can just using the index to access it, and use some other attributes. For example, we want to know what's the activation function. We can use the activation attribute to access that. So basically, it's tell you, okay, we're using the remove function. Yeah, so basically, if you want to inspect the elements, the components in the model, just try different different attributes. So here we can also get the weight and bias from this model. For example, just call this get weight method. It will return the weight and bias. So to put it simple, bias is that we have an intercept for each layer, and the weight is that for each neuron, and the second layer's neuron, they are connected with the edge, and that edge is it's so-called the weight. So we can check the weight and the bias after we build the model. We conveniently see that all the bias is 0. This is intuitive, right? Because we don't train the model. So ideally, they are initialized with 0, meaning, okay, we don't have any bias. But the weights, it's not all 0. So this is actually a question for you guys: why the bias is initialized at 0, but the weights is not? Yeah, so maybe to save some time, because we want the neural network to learn, so we need to take the derivative, right? But when we have the 0 as the initialization, you probably run into some numerical issues, like the calculation of derivative will be problematic. So usually the weight is randomly initialized, and then but it's not always it's not what equal to 0. So yeah, this is just for the consideration of training, and this is not controlled by ourselves. It's controlled by the model itself. So after that, we can we can start to think how to train this neural network. So we need to specify a optimization function. So here you can run you can call this Keras optimizer. They have a lot of other options of optimization, but here I use a stochastic gradient descent, which is a very popular one. And you can specify the learning rate to some value, and then try to train the model. So when you train the model, you first need to compile, specify the loss, because we have the binary, so it's a binary cross entropy. We have the optimizer. So after that, you can simply run model.fit with the training set. The epochs equals to 50 means you run through the whole data set 50 times. And the validation split equals 21. It's because we are going to, for each epoch, we need to split some data for validation purpose, so that the model learns how to update next step. So this is what's the output, and you can run it on your own terminal. It will output for each epoch and what's the loss or accuracy on the training on the training set, and what's the validation set, what's on the validation set. So after we train, we can see the accuracy is increasing. The tendency is increasing, but there's also some kind of fluctuations, because we know stochastical gradient descent is more like a stochastical process. It's not guaranteed that you always increase, but in general will tend to grow up. So after we finish the 50 epoch, we can see the accuracy on the training is 0.87. So still it's better than maybe better than the random guess. So we want to know whether what's the performance like in on the test data. So we can still, after we get the model, we can predict on the test data set, get the score, try the ROC curve and the PR ROC curve. So here is 24. So it's not perfect, not comparable to XGBoost or random forest, but it's still reasonable, because we know that our data is limited. The number of parameters is very high, like 500 parameters with only 400 samples. So it's kind of, yeah, we cannot expect more from this kind of this small sample size. So probably you can try later after the workshop, try to reduce the number of hidden layers. For example, just remove it, or just try to reduce the number of neurons in the hidden layers to see if you can make the neural network perform better when you test on the test data set. So the third thing is another example. So previously we do all the model training on the breast cancer, and we know that task is kind of simple. So almost all the method perform well, like AUC greater than 0.9. So we want to challenge some of the algorithms to see, okay, if we face this situation, will there be perform better? So one interesting example is that, okay, what if our data is not linearly separatable? For example, in this figure, we clearly see that this data set can be segmented into 4 different clusters, and the corresponding clusters, like the bottom left and top right, belongs to one cluster. They are labeled as 0, and the other 2 clusters, they are labeled as 1. So clearly we cannot draw a single line to separate those two clusters into like at the two sides of the line. So those are quite not linearly separable. And we want to evaluate, for example, the very simple one, logistic regression. What's the performance of the logistic regression if we train on this data? And we also want to know, okay, we know that decision tree probably is not an influencer because it's just trying to segment the whole space into different areas. So probably decision tree is capable of handling this. And for the supported vector machine, we know that if we just use the original support vector machine, it's still a linear classifier. Probably those are not suitable. And we also introduced support vector machine. They have the polynomial channel or the Gaussian radius kernel, like try to measure the similarities. Maybe those two can be useful in these tasks. But anyway, we just try to load the data into our Python object, and so here we just use a NumPy node text. So the data is actually just in the data folder. And then we do some exploration. For example, still just very similar what we did with the breast cancer, print the shape. First, you need to know, okay, how many samples, how many features in your data set. So this is what is the first step. You need to get familiar with your data. And you need to check, okay, whether your data set is balanced or not. So here, we can see the well balanced data with the neighbor 0, neighbor 1, equal number size, equal sample size. And you can also check for specific individual sample, what's the feature look like. It contains 2 features, and it has one label. So we actually want to predict this label based on the feature. And we see some pattern here. And so let's see if some algorithms can do it well. So first is still, before we do any training, the very first thing is that we split the data into training and testing. So this training is for model building, testing is to evaluate the learning algorithms. So we split them into still 20% for testing, 80% for training, and then we just visualize all the data using using the scatter plot. So right now we only have 2 features, so we can plot one feature's coordinate on X and one feature's coordinate on Y, and label each dot by the color each dot by its label. So here is what we did here. So we just split the data based on the label, whether they are equal to 1 or 0. So we gave it a different color. So this is what we did. And we try to train the logistic regression, very similar to what we did before, and plot the confusion matrix. So here, the results is kind of surprising that the logistic regression regressor doesn't work well, but it also makes sense because it's a linear classifier. So if we plot the ROC, we see a very strange phenomenon that we can increase the true positive rate increase first, and then somehow they pass the dashed line, which is a random guess. So this is also reflecting the pattern here. Right? We have one cluster that probably be well separated, but somehow this another cluster drives the ROC curve to another direction. So in the end, the AUC is smaller than 0.5. So as we see, the random guess is you only have AUC at 0.5. So this is smaller. So this is a kind of strange, denoting there is some strange pattern in your data. So as we said, we should consider to use a decision tree or maybe other classifier like random forest, XGBoost things, because they are capable of handling the division, region division problem. So here we just try this tree classifier with labels and the features, and see, okay, we have purely on the training data set, we can achieve 100% of accuracy. So this is sometimes this is good, which means, okay, you fit the data well, but sometimes you need to worry about it because this probably means, okay, you overfit the data. So, but before we test the data set, we can use some other approach to check whether it's overfitting. So the very first thing we can do is trying to draw the decision boundary of the decision tree. If you remember in the slides, we can see how one region can be divided by different steps. So that one is like the decision boundary. So here, what we did is a thing that we try to create a two NumPy arrange, and then try to for each of the value on the two-dimensional space, we can tell whether this region or this grid it belongs to class 1 or class 2. So basically, this is what we do. We will come back later about the usage of those things. So we try to plot a contour plot of this plot. So x and y is the value of the x and y, and z is like the denoting what class this region belongs to. And we see a very zigzag pattern, and this usually belongs to the data is overfitting, because if it's not overfitting, we should see some kind of clear pattern, not under those like single edges is not collected. Because when they are collected, this usually means, okay, there is some sample. Clearly, there are show some kind of outlier behavior, but the data still think the model still think they are good data, good labels. So they try to collect them, but we know those probably can be noise. So to go over the code of this usage, we use a NumPy mesh grid, which is trying to create a combination of x and y on the 2D plane. So this actually will return a two-dimensional A times B array, and each corresponding to x coordinate and y coordinate in an A times B grid. So just put it to simple. We create x as 0, 0.5, and 1. So after we do this NumPy mesh grid, we will end up with several values like this, and the y is still like a replicate of itself by 4 times, and those are the x and y values on this 2D plane. So this is what we do. And we also use the reveal function, which basically will flatten the nested or n-dimensional NumPy array into a flat array. So this it's used in the previous function from here. And we also use the NumPy.c, which will with a double with the underline score, so which will concatenate the columns horizontally. So if you see the SV reveal by reveal, and using this concatenation, you will end up with array that each element will have two values because they are concatenated the columns horizontally. So anyway, this is how we create the 2D plane, and the delta is actually the step length of the grids, so it can actually shows the resolution. So after that, we just create a function. So whenever we have a creator classifier, we can plot the decision boundary using this function. So this is what we have for the tree classifier. When the delta is 0.05, we see some nice pattern that they are not like a single edge showing the noise is also preserved in the model, but they show some blank. But if we increase the resolution, as we said, the delta is a step size, increase the resolution, then we still see such kind of single edges, which showing the model is overfitting. So to make our model less easy to overfitting, we can adjust a lot of hyperparameters. For example, we can reduce the depth of the tree. So here we can try max depth equals to 5, and when we plot, we can see the pattern is more reasonable. Like there is no noise preserved as the previous ones, and we can also try to print out the accuracy in the testing data in the training data. So previously, when we first tried, it's 100%, but right now it's like 92%. So this means the accuracy is decreasing, but that's not necessarily a bad thing, because we actually don't overfit that much. So the model can preserve preserve the information and ignore the noise. So it looks much better than previous one. So as I said, the SVM can also achieve the nonlinear separation. So there is two parameters you can tune. One is the C, which is, if you go back to the slides, we talk about the C is controlling the sensitivity to margin violation, and the gamma is controlling the influence of a single training example. So adjusting low C that will be less sensitive to misclassification. High C will be more sensitive to misclassification. And a low gamma will try to have a simpler boundary, and the high gamma will try to have a complex boundary. So usually you want to fix one and adjust another to find a good range, and then you can try other approach to find the combination of the C and gamma to achieve the best performance. So here we just show if we just train it, what would be like, for example, a really naive SVC default parameters achieves 96% accuracy on the training. And if we increase the gamma, this will result to the more complex boundary, which means it's more likely to overfit the data. So it achieves 100% accuracy on the training. And if we plot the boundary, it shows like this. And if we change other parameters, yeah, we actually try a lot, like C equals 1000, gamma equals 100. You can see a lot of isolation island in the plot. So this is also not good, because it's also a sign of overfitting. And then if we change the C to a smaller one, makes more sense. And we can also continue to try to change for different parameters. But this is just for one training. if we want to really tune the parameters, we need to have a validation data set that we have described yesterday, that we want to split the training set into two sets. One is the reduced training, you run the model, and one is validation, that you use to select what kind of hyperparameters you need to use. So again, we will just use a train and test split to further split the training data into training and validation. So for each gamma, we can put them into a NumPy array, and then for each iteration, we will use this the splitting repeatedly and then calculate the average. So this is the final accuracy on the validation set. We can see that when we increase gamma, we can observe there is a increase first and then decrease later. But if we just look at the training data set, the accuracy is always increased. That means with the validation data set is necessary. If we just look at the accuracy on the training, we will end up with a higher and higher gamma, and this actually will lead to overfitting. So this is a very different results if we look at the training and the validation accuracy. So we can also like print out the average across all the repetitions, still see the different accuracy on training and the validation. So lastly, we can actually have the k-fold of cross validation, which is implemented in the k-fold. And in this k-fold, we have the n splits equals to 10. That means we want to use a 10-fold cross validation, and we can write a program like by ourselves for loop to run it. But I think it's better just try to use the function provided by the sklearn. So basically, you input your classifier and your features, your training data, and simply use the CV equals to the cross validation you just defined, and it will return the final performance measurement. And you can actually specify what performance you want to obtain. I think the default is accuracy, but you can also play with the precision report, the point score. So I think that's all for today. We are on time, and yeah, I hope this one gives you more practical knowledge about how to use a package and how to train a model. So when you have time, you probably can just run it through and try to change some parameters, see how the performance goes. And I think that's all for today. I will see you tomorrow.